Oh, oh, is this thing on? Oh, okay. Sorry about that. We're starting lesson 5 right now. This is the last section of Unit 4. This is the Trapezoids and Kites. So we've done all the other quadrilaterals we're going to do. Trapezoids and Kites, the only one left. Let me recap where this fits in the hierarchy. This is that diagram. It's not in your notes, but it's a diagram I like to use that shows how the whole family tree kind of works for quadrilaterals. Remember, the top of this is the general, and the bottom, the farther we go down, the more specific we are. So square has the hardest definition to meet. Quadrilateral is just anything, generically, is a quadrilateral. We've spent all of our time so far this chapter talking about this. The new ones today are kite and trapezoid and isosceles trapezoid. Just so you know, they're kind of obscure. They're kind of, the cousins you never talk to, but that's where they fit. Okay. So you need to know what a trapezoid is. First of all, trapezoid in our book is defined as a quadrilateral with exactly one pair of parallel sides. That's a bit controversial. If you look this up on Wikipedia, you'll uncover one of the greatest debates in the geometry world, that trapezoid doesn't always have this definition in every context, but our book goes with this one. I kind of like the other one. We'll talk about that in class. Different teachers have different ideas, but we're going with the book. And the book says this, exactly one pair. So, in other words, these have to be parallel. These have to not be parallel. It hurts me to say that, but yeah, that's what we're going with. So that's why I've got this in here. And it's in the picture here in the definition that those are parallel. These aren't marked because they are not. We don't have a marking for not parallel, oddly enough. Guess who's right? Anyway, we're going with that. And we got some names in here. Kind of reminds me of isosceles triangle. These things that are parallel are called the bases. The ones that are defined to be non-parallel are called the legs. So yeah, trapezoid is not a parallelogram according to that definition. Again, it kind of burns when I say that. We are going to talk about something really quick here, though. Trapezoids can be a little more special. There is a isosceles trapezoid that's a little more special. Check that out as we go into this. If it has congruent legs, oh, you know what? I use this from a different book. Let me change this. Just realize our book defines this as a trapezoid that has these non-base sides as congruent rather than the angles. It's okay. That is not a controversy. That's a 50-50, 6 of one, half dozen the other thing. Oh, wait. Now I've resized things and nobody's happy. Just a second. Can I just move this? Okay, I guess that's going to work. Sorry, it's right on the edges there. I had to resize when I had to draw on it. Anyway, an isosceles trapezoid is a little bit more special. It's got, again, it's isosceles. It's kind of symmetrical. It's got congruent sides here on the parts that are not parallel. That should look pretty predictable to you because of what we know about isosceles triangles. All right, so most of you know what isosceles trapezoids are. There's some theorems that follow from them. They are special, so they get new properties, kind of like what happened when we started talking about rhombuses and rectangles. All right, there's 3 here with isosceles trapezoids. And the first one is if these sides are congruent, that proves, or we can show then the theorem is that the so what here is that these angles are congruent. That's kind of the big deal. And if those angles are congruent, it's going to turn out that these angles are congruent too. So that's all about angles. It reminds me of the ITB that we had from triangles. If the 2 sides are congruent, then the 2 angles are congruent. This just comes with 2 pairs, speaking to all 4 angles. Next one, if a trapezoid has 1 pair of congruent base angles, then it's an isosceles trapezoid. In other words, then these sides are going to be congruent. So it's just like the converse of 621. So both of these together kind of remind me exactly of the ITB for triangles. If 2 angles are congruent, then 2 sides are congruent. That's this one. And if 2 sides are congruent, then base angles are congruent. And we could call either pair of these angles base angles. Okay, that's all easier and more predictable than it sounds. Naming it won't be so bad either. We'll see in the formula sheet, or the theorem sheet. All right, 623. Gosh, that's a lot of theorems in one chapter. I think there's 3 more after this too. And they write this one as a biconditional already. That's nice. This property should sound a little fishy to you because it should remind you of rectangles. If we have an isosceles trapezoid, it turns out that the full diagonal lengths are congruent. That was also true in rectangles. Now the deal with rectangles was, the theorem that ended with this diagonal is congruent, it started differently. It said if a quadrilateral is a parallelogram, then the diagonals are congruent. So that was a different sort of if. This one is if we know it's a trapezoid, then, and we sort of know that the diagonals are congruent, then it's going to turn out to be isosceles. This is the most surprising by far out of these three, that isosceles trapezoid would have something so special about it. And it kind of overlaps with our ideas about what rectangles do. All right, construction time. Let me get the tools out. All right, this is saying construct an isosceles trapezoid using 6.21. So I'm supposed to use this principle to make it happen that it's isosceles. So if a trapezoid is isosceles, then each pair of base angles is congruent. So I'm gonna do it by constructing. I think what this means is, part of the biconditional here, is I'm going to construct it by having base angles congruent. I'll make base angles congruent, and that's just going to make it be an isosceles trapezoid. So the first thing I need is for it to be a trapezoid. So let's make parallels first. So I have a line here. I need to make a parallel. I don't want to get too far off the page here. So let's do this line. Let's say these are going to be the two corners even. And let's make a parallel. Well, you know what I could even do? I could even go so far as to say, here's the start of my next side. And if you remember constructing parallels, what that meant was we just constructed corresponding angles to be congruent, and we knew we had parallels. That was the easiest way to do it. So I'm going to make an angle here. I'm going to copy that angle at some random point up here. Oh, I should probably mark this point first. Let's say we're going to stop this madness right here. This will be the vertex of my trapezoid. I stopped it early because I stopped it this far low because I need to be able to have some angle to write on here when I do this copy. Hopefully this looks familiar too. Now I'm doing the Mr. Bean step where I measure this span. It's going to be about that big. I can't set this perfectly where I want to, but that's really darn close. You can tell what I'm doing. Maybe a little bit closer there. Oh, wait, now I got to turn it a little bit. Is that right? Gosh, I'm being picky on myself here tonight. Okay, and then put that right about there. And we see, oh gosh, you probably should watch this in fast motion. That's probably a little bit frustrating. Okay, and then right there. So that's where that angle goes. Let me get out my straight ruler cheater tool. All right, and then I'm going to draw this straight line here. So this is, all I've done so far really is create a parallel by doing corresponding angles here. But really, I've got three sides of the trapezoid here kind of already spoken for, so to speak. I know I've got this direction, this perfectly nice angle, so there's a vertex. I call the vertex there. I might as well call this a vertex. And remember this theorem 621 is I want to make an angle over here now that's congruent to this angle over here. Well, that's the same process I've been doing. I'm just going to copy this angle again. So, well, you know what I need to do? I need to get this span back. Whatever this compass size was, I need to get back to here. Maybe I should have done that when I had it set, but this is okay. This will work. Okay, and then do the span again. Yeah, copying three angles at a time is probably easier than copying one and then going back and trying to copy it again. So if I would have thought forward on that, it would have been a little better. Now here I'm copying an angle kind of in a mirror image. This feels a little backwards compared to the way you usually kind of copy-paste parallel angles. It's a little easier to keep track of what you're doing than what I'm about to do here, which is that. But I did the same process. Of course, I kept talking all the way through it, but the same process, and I just copied that angle there. So that's the same angle. I kind of missed here, but that's the same angle as you know, this and this. All three of these angles are congruent. I took this angle and I copied it here. I went back to this angle and I copied it here. But again, the mirror image makes it look a little harder to follow. But that's it. That's enough to show these 4 points that I'm, oh, here, I'll fix my little gap there. These 4 points here have to be the corners of an isosceles trapezoid. Okay, yeah, this tool's in the way now. Or I'll set up to the side. The mid segment, oh gosh, you can't really see that. Let me see if I can fix that. Are we still rolling? Oh, man. Sorry, I thought I paused it. Yeah, I'm trying to resize it. Okay, mid-segment of a trapezoid is the segment that joins the midpoints of the legs, right? That's just a term. We're just defining that. We had similar things in triangles, like we had medians and we had altitudes. This is one of those kind of things. So if I connect a, oh, man, I'm moving stuff all over the place. All right, we have a midpoint of a non-base side connecting a midpoint of a non-base side here. Again, those are called legs. Midpoint to leg, midpoint of leg to midpoint of leg, called midsegment. As you might imagine, we're not just defining this because it's fun and we need to use more words. We're defining this because it actually has some properties that are kind of interesting. If you can't tell by looking at this diagram already, it turns out midsegment is parallel to the other two lines. I don't know why we have this example here, and then they turn it sideways when they go to make the theorem. Anyway, this EB here is a midsegment of this big trapezoid. It's kind of a sideways trapezoid compared to the ones we've looked at so far, because the parallels are vertical here on the left and right sides. Anyway, so if E is a midpoint and B is a midpoint of those respective legs, then it's parallel. And the big so what, the big aha, the big surprise here is this. We actually know the length of EB. The length of EB is the average of the length AF and CD. So it's kind of like we do with coordinates. We add AF and CD and divide by 2. Or you can use this formula here, same thing. Half of the sum of AF plus CD. All right. I think that's it for isosceles trapezoids. Now we're on to kites. You know what? I can tell right now this is going to take more than the time I have left in the video. So I'll start part 2 with kites. Part 1 is ending now.